in 9.1, we actually derived the boundary layer, like the governing differential equations for the boundary layer theory for delta, the thickness of the boundary layer much less than the size of the object L, and we got these equations. Okay, so I'm going to write down those equations. I'm going to show you how we can actually attempt to solve those equations. So let's go to lecture 10 so far. So let's say solving boundary layer equations. So far we obtained del Vx over del x plus del Vy over del y is equal to 0. This is continuity equation. You can even derive this by using shell values. Vx del Vx over del x plus Vy del Vy over del y is equal to nu del square Vx over del y squared, right? And that's the x momentum equation. We said the y momentum equation, we made use of it, but we don't need to rewrite it because we made use of it to neglect the pressure terms, right? These are our boundary layer equations, momentum, for momentum transport. Now, our aim is to find out delta x, the boundary layer thickness, the velocity profile, Vx, x comma y, tau w, the shear stress at the wall, and the drag force. Okay, so we want to find out those things, and we're going to see that these quantities are related to thermal analogs of these quantities. We will use these boundary layer equations and appropriate boundary conditions to derive the velocity profile, which will be used to find the wall shear stress, which is a quantity of engineering significance. For instance, pumping a fluid over the wall requires overcoming the shear stress, right? It's analogous to friction acting on objects moving on a surface, right? So how are we going to do this? We will do this by integrating both boundary layer equations, in other words, the x momentum equation and the continuity equation across the boundary layer. When I say across the boundary layer, I mean from y is equal to 0 to y is equal to delta x. And this method is called the momentum integral method. So let's integrate the x momentum equation with respect to y from 0 to delta x. Okay, so our equation is going to be, so we had Vx, remember, del Vx over del x dy plus Vy del Vx over del y dy is equal to nu del square Vx over del y squared dy. And let's integrate it. And nu is a constant. I can take nu outside the integral. So I'm going to integrate from 0 to delta. So I multiplied by dy's. and I integrate it from 0 to delta. Let's call this equation 1. Let's focus on this term, the second term, and let's integrate it by parts. Let's write that term from del 0 to delta, Vy del Vx over del y dy is equal to, now you're going to think of this as u and this as dv, u dv, okay? So then you're going to have the uv, which is Vy Vx from 0 to delta, minus integral v du, which is Vx times del Vy over del y dy, okay? Instead of dvy, I wrote down del Vy over del y. And remember that while we are doing this, we are picking up a particular x value. So we are doing this integral along y direction, but we chose a particular x value. Okay, so we're not changing the x, but we're only changing the y. And this term is Vy Vx 0 to delta is nothing but Vy at delta, which is Vy infinity, times Vx at delta, which is Vx infinity, which we called as V infinity, right? Minus Vy at 0, Vx at 0. So they are actually 0 because Vy is 0 at y is equal to 0 because of the no penetration boundary condition, and Vx is 0 at y is equal to 0 because of the no slip boundary condition. So instead of that, you can write down Vy infinity, V infinity. So this term can go here. Okay. And let's write down these explicitly. Vy is equal to 0 at y is equal to 0. This we call as the no penetration boundary condition, meaning that if you have a plate, the fluid is not penetrating into the plate, meaning that the velocity along the y direction is 0. Okay. On the other hand, Vx is equal to 0 at y is equal to 0, and this is called no slip boundary condition, meaning that at the surface, the fluid touching the surface is just stationary, it's not slipping. Okay, it's not sliding around. Okay. Also, from continuity equation, this term del Vy over del y is equal to minus del Vx over del x from the continuity equation, right? So you can actually write it here. So thus, this equation becomes zero to delta Vy del Vx over del y dy is equal to Vy infinity, V infinity, plus, because this minus and this minus makes plus, so go from 0 to delta del V x over del x Vx dy, right? And substituting this into the integrated x momentum equation. Which equation is that? It's equation 1. It's this one. So we actually got this one. So now we can actually plug it in here. Okay, gives 2 times integral from 0 to delta Vx del Vx over del x dy plus Vy infinity V infinity, okay, is equal to nu integral 0 to delta del square Vx over del y squared dy. Let me know if you are not able to follow it. So basically, this thing we plugged in the place of this, right? So, oh, sorry, not in the place of that. We plugged in the place of this thing, okay? And we got this one, and we got another this one. So you have 2 of them, right? And then you have this term here as well. And then the right hand side is just fixed. So I didn't actually touch that. Okay. And the right hand side, you can play with that a little bit more. I mean, a little bit. Nu, oops, take the integral, that's basically double derivative, meaning that you take the integral, you just gonna find the first derivative. Or in other words, it's like 0 delta del over del y in parentheses del vx over del y dy. So you have this del over del y and dy here. They can cancel because you're not actually changing the x. So you're just gonna have this one as your function. So it's going to be nu del Vx over del y from 0 to delta. These are the boundaries of the integral. It's equal to minus nu del Vx over del y, estimate at 0. If you estimate this thing at delta, you get 0. The reason is because the velocity profile saturates y is equal to delta, meaning that the velocity does not change. The gradient is 0 beyond y is equal to delta. Okay, so let's say since del Vx over del y at delta goes to 0, this is the definition of the boundary layer things, right? We define the boundary layer as like beyond which the profile does not change anymore. Okay, and let's call this equation 2. And this is related to this quantity is related to shear stress, right? Because it's the velocity gradient multiplied by the viscosity, kinematic viscosity. So it should give you something proportional to the shear stress at the surface because you're calculating it at x is equal to 0. I'm sorry, y is equal to 0. Okay, any questions? Okay, now let us obtain the Vy infinity from the continuity equation. del Vx over del x plus del Vy over del y is equal to 0. Let's multiply by dy and take the integral similarly. Integral del Vx over del x dy from 0 to delta plus integral from 0 to delta del Vy over del y dy is equal to 0, right? And then let's keep this term on the left as the same. But the term on the right hand side, that's going to be just Vy estimated delta minus estimated 0. So you basically get Vy infinity at y is equal to delta, but Vy is going to be 0, so it's going to be minus 0. So you don't need to write it. Is equal to 0. Okay. Now we get this Vy infinity. Let's have a look at this equation 2. So we have this Vy infinity, and let's substitute it there. Okay. Substituting. Let's solve for the Vy infinity first, right? I mean, so thus Vy infinity is minus this thing, equals 0 delta del Vx over del x dy. Now, substituting Vy infinity into equation 2, we get, let's have a look at that here. It's 2 times Vx del Vx over del x dy, right? Plus the Vy infinity, which is basically this thing, minus 0 to delta del Vx over del x dy, but you also multiply it with V infinity, okay, is equal to the right hand side, this thing, minus mu del Vx over del y, estimated at y is equal to 0. Okay. From here, you can have a look at this thing, Vx times the derivative of Vx. It's basically the, well, actually 2 times Vx times the derivative of Vx. It's basically the derivative of the V squared x, right? Vx squared. And you have another del over del x. So basically, you can actually collect all the terms under the integral from 0 to delta, right? Dy is common in all. But we're going to take the derivative del over del x of the following things: Vx squared minus V infinity Vx. Okay, so the derivative of Vx comes from, comes from this term, derivative of Vx squared. And the derivative of this thing comes from these terms. And since the integral is with respect to y and the derivative is with respect to x, they are 2 different variables, independent or vertical or orthogonal variables. You can play with the position of the derivative. You can actually put it inside the integral or outside the integral, however you like. Okay. Okay. Good. Basically for this one, we are actually keeping it inside, right? We are keeping the del over del x always inside the integral. And we might not able to get it outside of the integral just because, see, there is this delta which actually depends on the x. Although the y does not depend on x, the boundaries of the integral depend on x. So it might not be a good idea to take the del over del x outside of the integral. So I pull my word back about that. The right-hand side is equal to minus mu del vx over del y at y is equal to 0. Now, as I said, you cannot take the derivative outside of the integral, right? So there is actually a law called Leibniz rule in calculus that you can make use of to actually get this derivative outside the integral. So let us use the Leibniz rule for differentiation. Differentiation under an integral. Okay, so let's remember that it says the following: if you differentiate with respect to x a function, the integral of a function, which is a function of x and y, along y, not along x, but the boundaries go from a to b, which are functions of x. Okay, and the Leibniz rule says that first you can take it inside, but take the derivative inside, but that's not going to be the only term. You should add some corrections to that. Del f over del x dy plus f of x comma b. Instead of y, you replace it by b. That's the first boundary, times the dbx over dx, minus the lower boundary is f x comma a this time. A is a function of x. Dax divided by dx. Okay, so that's the Leibniz rule for differentiation. So for our case, our f is vx squared minus v infinity vx, right? Our ax is equal to 0, the lower boundary, right? And our bx is delta x, right? And f of x comma b, you replace the y by b, which is you replace the y by delta, is equal to vx squared minus v infinity vx estimated at y is equal to delta, which is equal to vx estimated that delta is nothing but vx infinity, or we call it v infinity squared minus v infinity squared, which you get 0. Okay, fxb. And on the other hand, fxa in our case is vx squared minus v infinity vx estimated at a is 0, so estimated at 0. Y is equal to 0. And if you estimate vx at y is equal to 0, it's 0 from the no-slip boundary condition. Minus vx is also, so yeah, vx we said 0, 0 minus 0, you get 0 from the no-slip boundary condition. So for our case, d over dx, integral from 0 to delta, vx squared minus v infinity vx dy is going to be equal to integral from 0 to delta del over del x vx squared minus v infinity vx dy. And we don't have the other terms, right? See, this one is going to be 0, this one is going to be 0 for our case. We said that, right? So you only have this term for this particular case. So for us, it's basically it's the case that we can actually take the differentiation within the integral and take it out of the integral. So so substituting this into 3 gives I didn't label it 3. Okay. So this is my 3, equation 3. Let's substitute it there. What do we get? Yeah. d over dx integral 0 to delta vx squared minus v infinity vx dy, the left hand side, is equal to negative mu del v y, del vx should be over del y at y is equal to 0, right? So this is our governing equation, integral equation. We call it von Karman momentum integral equation. Okay. Now, what does it say? It says the following: if we can find Vx as a function of y, that means we can obtain the wall shear stress, right? This is going to be the wall shear stress, or at least proportional to that. So if you know the Vx is a function of y, we can estimate the left hand side and right hand side. So let's write it inverse. If we can find Vx as a function of y, we can obtain the wall shear stress. Now, one point, well, actually, we didn't need this equation to tell us that if you find the Vx as a function of y, we can obtain the wall shear stress, because you already know it from the Newton's law of shear, right? So the tau is equal to negative mu del Vx over del y. You already know that. But this equation particularly tells you that you have some equation upon which, like if you solve upon which, is going to give you the velocity profile. So basically, either way, if you know the functional form, or if you test a velocity profile, you can actually see if the equation is satisfied. You know that the velocity profile is correct. So this is a additional information about our velocity profile. Okay, it's not telling particularly that the wall shear stress can be estimated from the velocity profile. Let's have a look at the left-hand side, particularly. That's equal to d over dx, integral from 0 to delta, vx squared minus v infinity dx, right, dy. And that's equal to, you can take under the common prefactor of vx is the common prefactor, vx minus v infinity dy. And then you can divide and multiply it by v infinity squared to non-dimensionalize what's inside the integral, v infinity squared d over dx, and v infinity is a constant, so I can take it out of the integral and also out of the derivative. V x over v infinity times vx over v infinity minus 1 dy. Okay. So what does this equation tell us? Now, it tells us that we can actually come up with some guess function, okay, and or assume or guess the function for vx over v infinity, and we can plug in and see whether it works. And at least we can actually write down a form. Let's say, for example, let the function be quadratic or third order or a quartic polynomial, whatever, right? So you can come up with some like y over delta versus vx over v infinity. Okay. Imagine that you have this actual velocity profile. Suppose this is the actual velocity profile. This is the y-axis, right? So basically, this looks like the profiles look like this, right? As you have seen in fluid mechanics course. But you can assume like a coarser y instead, like this. Assume a functional form, right? What it tells you that the assumed functional form is going to have some error associated to that, right? But because we are integrating this times 1 minus this, or this minus 1, it doesn't matter, the error is going to be something like positive error accompanied by a negative error, which should actually partly cancel, right? So you can actually reason that the functional form that you come up with should satisfy this integral equation to up to a good approximation, just because you're integrating vx over v infinity times 1 minus vx over v infinity. Okay, so if you're actually thinking about the absolute values, because 1 is larger than the vx over v infinity. So you're going to get a larger number for the first one, smaller number for the second one, so they actually should cancel out partially. Okay, let's summarize what I said. So the assumed functional form of the velocity profile will have an error associated with that integral. Because we are integrating Vx over V infinity times 1 minus Vx over V infinity. I'm writing it in positive values so that both are positive. I know that Vx is smaller than V infinity, so this term is also positive, this term is also positive. The errors in the integral for Vx over V infinity and 1 minus Vx over V infinity. So if the error associated to this is plus E, the error associated to this is going to be minus E. So they actually would cancel up to quadratic terms, right? If the error is, for example, 0.1 minus 0.1, after multiplication, the error is going to be something around 0.01. So it's going to scale with the square of the error, so which is going to make the error smaller, right? Let me show you algebraically. If you have a number x plus e times x minus e, if this is the error actual number, this is the error associated to that. Now you get the following: x squared, right, minus e squared. So you don't have the plus e or minus e term. So the error associated is going to scale with the square of the e, which means it's going to actually attenuate or reduce the error, right? That's what I mean. So the errors in the integral for blah blah will partly cancel out, right? Partly cancel out. So how about we assume some functional form? Let's assume, for example, a third order polynomial. So we are making an assumption here. We are making an approximation. We're going to assume that the velocity profile is a third order polynomial, but any error associated to that is going to be squared, meaning that the error is going to be less than the error associated with the velocity profile. Okay, so Vx over V infinity, let's imagine that it's a0 plus a1 y over delta plus a2 y over delta squared plus a3 y over delta cubed. The reason I actually assumed third order polynomial instead of fourth or fifth or sixth order polynomial, because I wanted to have like 4 coefficients, like 4 unknowns. Why do I want 4 unknowns? Because I will have 4 boundary conditions. Have 4 boundary conditions, as we will show below. So third order, because, okay, what am I doing here? use the technology. Okay, good. So boundary conditions are as follows. The first one is at y is equal to 0, Vx is equal to 0. This is called the no-slip, right? 2, at y is equal to delta, Vx is equal to V infinity. 3, at y is equal to delta, the velocity profile does not change anymore, so it's going to look like del Vx over del y is equal to 0. 4, the x momentum equation is, it gives us another boundary condition at x is equal to, sorry, y is equal to 0. Vx del Vx over del x plus Vy del Vx over del y is equal to mu del square Vx over del y squared. So that means the following: since at y is equal to 0, Vx is equal to 0, and Vy is equal to 0. So if you plug in these zeros here, you find that the left-hand side is 0, thus the right-hand side must be 0, right? So from here you find that this is 0, or in other words, del squared Vx over del y squared must be 0 at y is equal to 0. So this is your fourth boundary condition. Okay. Now let's apply the boundary condition 1 first. You get y is equal to 0, Vx is equal to 0. So all these cancel, right? So you get a0 is equal to 0. Correct? Let's apply boundary condition 4. Now, del over del y let's first take the derivative of Vx over V infinity. Del over del y Vx over V infinity is equal to, from here, it's the first derivative of this thing. It's basically a1 over delta plus 2a2 over delta plus 3a3 y squared, so there's y here, over delta cubed. This is delta squared. Okay, let me write it here. 2a2 over delta squared y plus 3a3 over delta cubed y squared. Okay, and the second derivative, same thing, gives you 2a2 over delta squared plus 6a3 over delta cubed y, and the left hand side is 0 at y is equal to 0. So 0 is equal to 2a2 over delta squared. From here, we find that a2 is also 0. So the equation becomes Vx over V infinity is equal to a0 is 0. We start with the a1 term, a1 y over delta, plus a2 term is 0, so we have a3 y over delta cube. Let's apply boundary condition 2. One, right? Boundary condition 2 says that Vx is equal to V infinity, meaning that Vx over V infinity is 1. The left hand side is 1. 1 is equal to, instead of y, I'm going to plug in delta, so I get 1 is equal to a1 plus a3. It's one equation. Another equation is if you apply boundary condition 3, that's the last one that's left. At y is equal to delta, del Vx over del y is 0. We already calculated del Vx over del y. This one must be 0, right? Y is equal to delta. So you get 0 on the left hand side, and the right hand side is a1 over delta plus, we don't have the a2 term, we have only the a3 terms, 3a3 over delta. And if you multiply by delta and take the 3a3 to the other side, you get a1 is equal to minus 3a3. And if you actually plug this in here, you would get 1 is equal to minus 3a3 plus a3. From here you get 1 is equal to minus 2a3. From here you get a3 is equal to minus 1/2. And since a1 plus a3 is 1, a1 plus minus 1/2. From here you get a1 is equal to 3 3/2. Okay. Thus, our equation is Vx over V infinity is equal to 3 over 2 y over delta minus 1/2 y over delta cubed. Okay, so that's the approximate velocity profile approximated up to third order polynomial. Okay, any questions so far?
Yeah. How did you know that you're gonna have four separate like y's, four separate constants?
For like a1, a2, a3, a4, you mean?
Yeah. How did you know you're gonna have four boundary conditions? Yeah.
How did I know? Oh, okay. So is there any other boundary conditions that you can come up with? We only have 4 because I only have like 2 interfaces, and for each interface I have 2 boundary conditions. I know that, right? So imagine here we are actually particularly interested in this region. I know what is the boundary condition here, and I know the boundary conditions here, and I can count them. I have 4 of them, right?
Okay. Thank you.
I mean, was I able to answer your question, or
Yeah.
am I
Yeah.
misunderstanding? Am I misunderstanding what you mean?
No. I think I understood you.
Okay, so we have actually 4 boundary conditions. I guess we cannot come up with any. I mean, you can come up with one more boundary condition, like but you already have used it, right? So we said that, so you're using the no slip one, but we are not using the no penetration one, but we are making use of the no penetration boundary condition here, right? So I don't have 5 because I made use of it already. So it incorporates that one here. And you will see that if you plug in, it's automatically going to satisfy that one. At y is equal to 0, you're going to see that, no. So we don't have an idea about Vy. So although at y is equal to 0, Vy is equal to 0, you cannot use it because we are actually trying to find out the functional form for Vx. That's why actually we use the x momentum equation so that we make use of the Vy to give us an information about how the profile is changing. Okay.